constructing a frequency distribution. This is for the example of the 18 students who were asked how many hours they worked in a day. So our first column would be our data values, the number of hours. They should span every possible response. Since this is quantitative data, we should keep them in order. The smallest data value in the set was 2, the largest was 9, so we should have every value from 2 to 9 represented. Now, there is a column that is sometimes employed. In this case, the data given was not in any particular order. It seems to be just written down in the order that it was collected. So it may help, particularly if it's a larger data set, to add a column that says tally. This column isn't actually necessary to a frequency distribution. It really is only included perhaps when you're making the distribution. If you were, say, a statistician and you were at a job, you would not include this in a table you were presenting, but it can be useful for helping to get the actual quantity, particularly when the data is out of order. So we could just go down the line and make a tally mark for each value that we see. So the first value in the table, and I'll go across the top row, and then the second and then the third. The first value was 5. We then had 6, and then 3, another 3, a 2, and a 4. The second row, 7, 5, 2, 3, 5, 6. The third row then is 5, 4, 4, 3, 5, 9. Very simple, and then we can actually write in the frequency. Simply by counting the tally marks. There were 2 responses of 2 hours, 4 responses of 3 hours, 3 responses of 4 hours, 5 responses of 5, 2 responses of 6, 1 response of 7, 0 responses of 8 hours, and 1 response of 9 hours. Now, I would remind you also that the sample size should be the sum of the frequencies. This is a particularly good idea, especially if it's a large data set, if you are using the tallies. If we know that the sample size is 18 beforehand, what we can do is check and make sure that all of our frequencies added up together actually equals our sample size of 18. As mentioned in the PowerPoint slide, lowercase n is the variable used for sample size. This is the Greek capital letter sigma. It is used in mathematics to denote a sum. So this is literally telling us, take the sum of the frequencies. Literally add them up. 2 and 4 is 6, plus 3 is 9, plus 5 is 14, plus 2 is 16, 17, 18. Perfect. That is exactly the sample size that we knew we would get. Now, relative frequency. Remember that relative frequency is for any response or data value is the frequency of that response divided by the sample size. So it's important that we know the sample size, and this problem did tell us beforehand. We should still add it up, as I said, to make sure that we have the correct sum here. If we got 17 or 19, it would mean we were missing one or made one too many tally marks somewhere. So we can go down the line now. The frequency here is 2 out of 18. Now, unlike the previous example on the PowerPoint, this gives us a repeating decimal. It's got an awful lot of decimal places, even if it has a finite number, but it just has too many to really be workable. The general rule of thumb for relative frequencies is 3 or sometimes 4 decimal places. 3 is appropriate, I think, in most cases. We will follow typical rounding rules, so we can use a calculator to do 2 divided by 18, and we get 0.1111, just a whole bunch of ones going on forever. So if we round that to 3 decimal places, we will get 0.111. For the data value of 3, there were 4 such responses. So the relative frequency of 3 hours is 4 out of 18, which again, from a calculator, would give us 0.2 repeating. We can round that off to the 3rd decimal place and it gives us 0.222. The next has a frequency of 3, so we have 3 over 18. Again, we can always use a calculator for this. Now, this is actually going to give us 0.16 repeating, so we have a 1 and then just 6s forever. So that should round up to 0.167. Five out of 18. Again, we use a calculator to get this. In this case, we would get 0.27777, etc. So this would round up to 0.278. The next frequency is 2. So 2 out of 18 is, like before, 0.111. 1 out of 18. Now, this would give us 0.055555. So, we again round it, and it becomes 0.056. 0 out of 18 is, of course, 0. And once again, we have 1 out of 18. Which, like before, will round to 0.056. Now, that's all we actually need as far as the relative frequencies, but much like summing the frequency column, this provides us some level of error checking. The sum of the relative frequencies should be equal to 1. Now, we have to keep something in mind here. Each of these ended up being rounded to 1 degree or another. These were rounded down, some of them were rounded up. Rounding actually changes the value. This shouldn't actually be a 7 here. This was 0.166666666, etc. So we actually changed the value in this place by rounding up. One of the reasons why rounding is something that should not be done casually. But we have to understand that because we're using values that are not exactly the right values, the sum may not add up exactly the way it should be. So, again, we can pull out a calculator and add these up. And what we would actually get here is 1.001. So again, not exactly 1. We're a little bit off, but that is due to the rounding. Some of these were rounded up a little bit, some of them were rounded up a little more, some of them were rounded down a little, some of them were rounded down a little more. Now, even in a case where we round down, we are changing the value here because there are supposed to be other 2's behind that. By cutting them off, we are, again, actually changing the value that we are using there. So as long as we're within 1 or 2 1,000ths, then we're pretty good. We can rest assured that that's accurate. It's one of the reasons why we might always write the fractions. Since the fractions actually are not rounded in any way, we can actually just add the fractions, which is easy because they all have the same denominator. And the fractions should at least come out to be exactly 1 every time. The decimals, if there is some rounding, may be a little bit off. You may get something like 0.998 or 1.001 as we see here. As long as it's really close, not 1.1, not 0.8, we're rounding to 3 decimal places. The only place we should see a difference then is in the 3rd decimal place, and only by 1 or 2. So again, it might be 1 1,000th too big, or 2 2,000ths too big, or it might